In this video, I want to talk a little bit about Newton's first law of motion. And this is a translation from Newton's Principia from Latin into English. So the first law, everybody persists in a state of being at rest. So state of being at rest or moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. So another way to rephrase what they're saying is that if there's something, everybody persists, so everything will stay at rest or moving with a constant velocity unless it is compelled to change its state by force, unless it's acted on by a force, especially an unbalanced force. And I'll explain that in a second. So if I have something that's at rest, so completely at rest, so and this is something that we've seen before. Let's say that I have a rock. Let's say that I have a rock someplace. I have a rock someplace, and it's laying on a field of grass. On a field of grass. I can keep observing that rock, and it is unlikely to move, assuming that nothing happens to it. If there's no force applied to that rock will just stay there. So the first part is pretty obvious. So everybody persists in a state of being at rest. I'm not going to do the second part, except insofar there's some force being applied to it. So clearly a rock will be at rest unless there's some force applied to it, unless someone here tries to push it or roll it or do something to it. What's less intuitive about the first law is the second part. Everybody persists in either being in a state of rest or moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. So Newton's first law, and I think I should do a little aside here, because this right here is Newton. This right here is Newton. And if this is Newton's first law, why do I have this huge picture of this guy over here? Well, the reason is because Newton's first law is really just a restatement of this guy's law of inertia. And this guy, another titan of civilization, really, this is Galileo Galilei. Galileo. And he is the first person to formulate the law of inertia. And Newton just rephrased it a little bit and packaged with his other laws. But he did many, many, many other things. So you really have to give Galileo credit for Newton's first law. And so that's why I made him bigger than here. But I was in the midst of a thought. So we understand if something is at rest, it's going to stay at rest unless there's some force that acts on it. And in some definitions, you'll see unless there's some unbalanced force. And the reason that's why they say unbalanced is because you could have two forces that act on something, and they might balance out. For example, I could push on this side of the rock with a certain amount of force. And if you push on this side of the rock with the exact same amount of force, the rock won't move. And the only way that it would move if there's a lot more force on one side than on the other side. So if you have an unbalanced force. So if you have a ton of, and maybe the rock is a bad analogy. Let's take ice, because ice is easier to move, or ice on ice. So there's ice right here. And then I have another block of ice sitting on top of that ice. So once again, we're familiar with the idea if there's no force acting on it, that ice won't move. But what happens if I'm pushing on the ice with a certain amount of force on that side, and you're pushing on the ice on that side with the same amount of force? The ice will still not move. So this right here, this would be a balanced force. A balanced force. So the only way for the ice to change its condition, to change its restful condition, is if the force is unbalanced. So if we add a little bit of force on this side, so it more than compensates the force pushing it this way, then you're going to see the ice block start to move, start to really accelerate in that direction. But I think this part is obvious. Something that's at rest will stay at rest unless it's being acted on by an unbalanced force. What's less obvious is the idea that something moving uniformly straight forward, which is another way of saying something having a constant velocity. Constant velocity. What he's saying is that something that has a constant velocity will continue to have that constant velocity indefinitely unless it is acted on by an unbalanced force. And that's less intuitive because everything in our human experience, even if I were to push this block of ice, eventually it'll stop. It won't just keep going forever. Even assuming that this ice field is infinitely long, that ice will eventually stop. Or if I throw a tennis ball, that tennis ball will eventually stop. Even if it'll eventually grind to a halt. Or if I roll a bowling ball, or if I anything. We've never seen, at least in our human experience, it looks like everything will eventually stop. So this is a very unintuitive thing to say, that something in motion will just keep going in motion indefinitely. Everything in human intuition says if you want something to keep going in motion, you have to keep putting more force, keep putting more energy into it for it to keep going. Your car won't go forever unless the engine keeps burning fuel and to drive and consuming energy. So what are they talking about? Well, in all of these examples, and I think this is actually a pretty brilliant insight for all of these fellows, is that all of these things would have gone on forever. The ball would keep going forever. This ice block would be going on forever, except for the fact that there are unbalanced forces acting on them to stop them. So in the case of ice, even though ice on ice doesn't have a lot of friction, there is some friction between these two. And so you have, in this situation, the force of friction is going to be acting against the direction of the movement of the ice. And friction really comes from at an atomic level. So if you have the actual water molecules in a lattice structure in the ice cube, and then here are the water molecules in a lattice structure on the actual kind of sea of ice that it's traveling on, they do kind of bump and grind into each other. Although they're both smooth, there are imperfections here. They bump and grind. They generate a little bit of heat, and they'll essentially be working against the movement. So there's a force of friction that's being applied to here, and that's why it's stopping. Not only a force of friction, you also have some air resistance. The ice block is going to be bumping into all sorts of air particles. It might not be noticeable at first, but it's definitely going to keep it from going on forever. Same thing with the ball being tossed to the air. Obviously, at some point, it hits the ground because of gravity, so that's one force acting on it. But even once it hits the ground, it doesn't keep rolling forever, once again, because of the friction. Because of the frictions, especially if there's grass here, the grass is going to stop it from going. And even while it's in the air, it's going to slow down. It's not going to have a constant velocity because you have all of these air particles that are going to bump into it, and exert force to slow it down. So what was really brilliant about these guys is that they could imagine a reality where you didn't have gravity, where you did not have air slowing things down, and they could imagine that in that reality something would just keep persisting in its motion. And the reason why Galileo, frankly, was probably good at thinking about that is that he studied the orbits of planets. And he could, or at least he's probably theorized that, hey, maybe there's no air out there, and that maybe that's why these planets can just keep going round and round in orbit, and their speed, because their direction is changing, but their speed never slows down because there's nothing in the space to actually slow down those planets. So anyway, hopefully you found that as fascinating as I do, because on some level it's super duper obvious, but on a whole other level it's completely not obvious, especially this moving uniformly straight forward. And just to make the point clear, if gravity disappeared and you had no air and you throw a ball, that ball literally would keep going in that direction forever unless some other unbalanced force acted to stop it. And another way to think about it, and this is an example that you might see in everyday life, is if I'm in an airplane that's going at a completely constant velocity, and there's absolutely no turbulence in the airplane. So if I'm sitting in the airplane right over here, and it's going at a constant velocity, so constant velocity, completely smooth, no turbulence, there's really no way for me to tell whether that airplane is moving without looking out the window. Let's assuming that there's no windows in that airplane. It's going at a constant velocity and there's no turbulence. And let's say I can't hear anything, so I can't even hear the engines. There's no way for me to sense that the plane is moving, because from my frame of reference, it looks completely identical to if I was in that same plane that was resting on the ground. And that's another way to think about it, that it's actually very intuitive that they're similar states, moving at a constant velocity or being at rest. You really can't tell whether you're one or the other.